Hello, 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 hello. Uh, how's it going, everybody? Hey, you know what? How does this work? I basically had to do this background today. Um, I basically had to because it's so fitting for what the problems we're doing today. I just, you know, I had to basically. But anyway, what new salmonella video? What was the last one? He hasn't posted for 3 weeks ago. Huh. Okay. Well, new salmonella video. I guess I'm watching that later. But anyway, hello everybody. Welcome back. We are gonna be streaming some LeetCode today, and it's gonna be a bit of a shorter stream, so because I have something to do at 8. Um, so we better get started earlier than later. Um, yeah. So, okay. Life updates. I went to beach volleyball on Tuesday, and that was pretty fun. And I went to a salsa class yesterday, and that was also pretty fun. And I'm going to like another salsa social today. So, um, I don't know. I think my plan was to like check them out both, like the both classes, like the beach volleyball and the other one, and then my plan was to, if I like both, just stick around with both. But I don't know if I can handle doing both of those in a week. So I might just start with the beach volleyball, and if I have extra time, I'll sign up for like the salsa classes. But the salsa class I had yesterday was really fun. I learned some stuff. It was like a beginner's class, so some of the stuff I knew already, and like those people had been there for 3 weeks, and I felt pretty on par. Um, but yeah, no, I like that. I still learned a couple new things, and I mean, I always like dancing. And for the beach volleyball class, channel disconnected, updated so your next stream goes there. Am I not live on LinkedIn right now? I should be. Yeah, okay. And then beach volleyball also like it was an intermediate class. I didn't want to sign up for the advanced because sometimes advanced is kind of crazy, but I think I am gonna end up sticking with advanced, just because I think I'm a little bit ahead of the intermediate group, but I still want to like keep practicing a lot. So that's what's my last week has been besides work. So it's been pretty fun, pretty full with stuff. I've also played some board games at work, and I won Eclipse. I've been playing Eclipse, which is a pretty fun board game. But yeah, anyway, that's it for me. I am going to just do our kind of card today and then get started with the problems. We'll solve two, and then I'll head out. Yep. Okay, so let's get started with the Lorcana card of the day. Have we done this one before? You know what? Don't remember. Doesn't matter. This is Sisu, Daring Visitor. It's a 3-cost and inkable. It's a Storyborn hero, deity, and dragon. And it's a one strength, 1 willpower. It has evasive, and it says when you play this character, banish chosen opposing character with 1 or less. It's by artist Otto Paredes. It's card 123 out of 204 in English from set 4, but this got reprinted in set 9, I believe. So I think it's still legal. Let's see. Yeah, set 9. So it is still legal. And a quest for 1. So this card, this is from Raya the Last Dragon, which I still have to watch. I haven't watched it. Like it's this dragon, I guess. Yeah, I haven't really watched it, so I don't know how it goes. But this card is really good, and it was even better before. But I'll go over that in a second. But this card, it's an inkable. It costs 3. It's pretty expensive for a 1/1 body, but it has evasive. That's a little bit of a plus. But then this is the ability that matters. When you play this character, Banish shows an opposing character with 1 strength or less. That is very good removal. Namely, right now, for example, there's like sometimes toys are played. So if let's look at Toy Story. There is the 1/5 Woody. This one. It's a 5 cost uninkable that shifts for 3, and it's pretty good engine. It has 5 strength, so it's a little bit sticky. It's hard to get rid of. So with this Sisu, you can just get rid of it for 3 immediately. Like, no questions asked, just get rid of it. Which is pretty good. Other cards that you can get rid of with that are... Let's see, some expensive cards you can get rid of. You can get rid of like a Lenny, which is pretty good. This is the main one I thought of, but okay, let's see. If we look up 1 or 0 strength, and then cost, I don't know, anything that's more expensive than it is. 4, 5, 6, 7. Oh, okay, I have a really good one. Dale. Dale's a really good target to get rid of. Zipper's a really good target to get rid of. This is a really good target to get rid of. This is a good target to get rid of. This is a good target to get rid of. Like, there's a lot of good targets for it. Let's see if only sets Fable, Winter Spell, Attack of the Divine, Worlds Unknown, and this. Okay. Yeah, so the main targets are like Dale and the Woody, which are in the zipper. Yeah, those are pretty good targets to get rid of with Sisu. Cost 3, you can also get rid of the Lenny, this Peter Pan. And I was saying that before it was even better because we had this card. So red was really powerful before. I think the most powerful deck before was red purple. And it was because you had this Sisu to get rid of one cost or less, and then you could shift onto this one, and then you can banish not only one character, but all opposing characters with 2 or less. So it's like almost like a board wipe. Like there were cards where you could reduce the strength of like your opponent's cards, and so you could pretty much get rid of all their cards with this shift. So this used to be pretty good, but this card is not on rotation anymore, so now it's only this, which not horrible, not great. But anyway, today's card is really good. And with that being said, let's start doing LeetCode. Okay, number of islands. It said, see, I don't know. I don't think there's anybody watching, right? Or maybe, if you're watching, just send a message. But I don't know if this like the count of how many viewers there is. Like, is it live? I have no idea. But okay, let's do some LeetCode. This is from last stream. Okay. Did I commit? I don't think I committed. So let's do this, and I think I have some, yeah, I have all of these in there, but whatever. That string, what do we do? Wait. So I didn't do this properly. Get restore minus minus staged everything. Okay. And I have to remove all of these. To remove files from. But okay, but something changed. I remember when I added the. Yeah, because I had all these untracked files, and then I only had these, so I did do it properly. The other thing is that the ones that were tracked already. How to remove files from Git that I added to Git ignore but were tracked already. Git rm minus minus cached. And I have to add R here. Git status. Okay, and then git add period, git status. Those are all deleted, and then we have all these new files. I updated my program.cs, and I connected all of these. Okay. So maybe git diff. Git diff. What is it? Head. There you go. So I added those services as singletons, and then I connected. Right, that makes sense. Git commit add vector db and embeddings model as singletons. Git push. Okay, cool. So now we exit from here, and now we're at LeetCode again. So I don't think we really need these windows. Shut them down, and okay, then let's go actually solve the problem. So we're starting with number of islands. Oh, the next two problems are kind of pretty good in terms of like what it teaches us for theory, but I'll give them a read. So 200, number of islands. It's a medium problem, and it says given an n by n 2D binary grid, which represents a map of ones that represent land and zeros that represent water, return the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume all four edges of the grid are all surrounded by water. So what does that mean? So they give us this grid. Now, ones represent land and zeros represent water. And then you have to determine how many islands there are. All four edges of the grid are all surrounded by water. Okay. How many islands there are in total, right? So, let's do a little paint representation because they didn't provide us an image with this. And I think it's easier to understand if you have an image. Okay, so this is the representation they give us for the grid, but we can draw it as an island, and I'll try to. So we have 1, 2, 3, 4 rows and 5 columns. 1, 2, 3, 4, 5. Okay. So our island looks like it tells us this is land. Goes to 1, 2, 3, 4, 5. Okay, so we actually need, I think, a couple more. Anyway, so we do 1, 2 right here, and then we go 2 to the right, and then we go. That's too close. Wait, sorry. It's 1, 2, 3. So it's from here. So we go 1, 2, then we go up 2. Then we go to the right, then we go down 1, then we go to the right, and then we go up, and then we just close it. So this is our land. Let's see. There we go. That's our land, and then the rest is our water. Okay, so that's what it looks like. And that's like how many islands there are. Well, we can count there is just one, just this whole block, because it's all connected land and it's surrounded by water. And it says to assume that this is outside of the grid is also water. So this is one island. But let's say they give us this one. If they give us that one, then we have 1, 2, 3, 4, 5, and then we have 1, 2, 3, 4, 5. So we have one island here, then another island here, and then another island here. So we have 3 total islands. Please note that they do not connect diagonally, so this is not a connection. And so we have 3 islands. I'll color them just for clarity's sake, but we have 3 islands. So we have to count the amount of islands. How are we going to do this? We're going to do this with, we've done it before, and this is with using DFS. You might be able to do it with BFS. I don't know. This is the way I'm thinking about it. But basically, to find the amount of islands, we're gonna go over the grid, just from top to bottom, left to right. And then once we get to a 1, we're gonna explore all possible paths. We're gonna explore the whole island basically. So we're gonna go here, we're gonna go here, we're gonna go to all adjacents, and then from here. Actually, if we're doing BFS, then be like here, 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 DFS, sorry. And so once we explore all this, we keep checking and we add them to like an array of visited. So once we've explored all of this, we start checking the rest of the array. So we check the first one. We go here. Have we visited it? Yes. So we don't visit it. Have we visited it? No. But it's a 0, so there's nothing to explore. We only explore once. We keep going. We visited this one. We visited this one. The 0, 0, 0, 0, 0. We haven't visited this one, to DFS. So we start here, and then there's nowhere to go. So that's another island. And then we do skip, 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 skip. We get to here. How we explored it? No. We visit it, and then we visit its adjacents, which there's only one, and that's another island. So there's 3 islands total. So basically, whenever we get to a 1, we explore all of its neighbors and the neighbors of its neighbors, and then we add them to a visited, and then we explore the rest of the matrix. And if we see a 1 we haven't visited, that means that's another island. Because if it was part of a previous island we visited, we would have been able to connect it and it would have been visited already. But since we haven't visited it, we know that it's isolated from all of the other islands we visited before. I hope that makes sense. I'm rushing a little bit today, but it's not too bad, I think. Okay, so this is, what is it? A graph problem. And it's problem 200. Graph / 200.cvp. Okay, and now we go here, copy this, paste. So let's write our function for DFS, which is very simple. So we do void DFS, and what do we receive? We receive a grid. And we receive an X position and a Y position. And then we're gonna have a visited matrix here. Let me call it visited. So at the beginning in num_islands, we're gonna initialize that vector. So visited is gonna be equal to new vector, or actually I think we can do vector of char, which is gonna have grid.size element, and we're gonna initialize it with a vector of char with grid 0.size elements. That's how we initialize our visited vector, and it's going to get initialized every time we call this function. And now in the DFS, we have a grid and we have X and Y. So how do we want to do this? So we have for the number of options for like the adjacent, we have 4 options basically. We have x plus 1, x minus 1. Sorry, no, it's a pair of xy coordinates. So x plus 1, x plus 1y, right? Then we have x minus 1y. Then we have x and y plus 1. And then we have x and y minus 1. So we can do this manually probably. Okay, so here we need to visit those 4 probabilities. So and we first have to check if they're inside the grid. So if x plus 1 is less than grid.size, then we can visit it. So we do, and also every time we visit a node, so getting into this DFS function means we're visiting that node. So we say visited of x, y is going to be equal to true. Also, this is all going to get initialized. I think it does by default, but we're going to initialize it to false. So every time we come into this function, we initialize the current node as true because we visited it. And now if x is inside grid.size, then we do DFS with grid, x plus 1, and y. That's the first option. Now, if x minus 1 is bigger than or equal to 0, then we do x minus 1. And now we copy this, we paste it. Now, oh, we have to check another thing, so we're not visiting. Okay, so with DFS, you need to do something, and that is you need to keep track of which ones you visited and not visit them again. Because if you're doing what I'm doing, where you visit all your neighbors, you say you start here, then you go here, and then okay, you start here. You have 4 neighbors, 1, 2, 3, 4. Let's say we check this one first, so we go here. Then this has 4 neighbors, 1, 2, 3, 4. Let's say we check this one first, so then we go back, and then we go back, and then we go back. So we just stuck in an infinite loop. So you have to keep track of which ones you visited, so you don't go back. Okay, so we only do the DFS if x plus 1 is less than grid.size and visited, and we haven't visited the position x plus 1, y. Okay, same with this one, and we haven't visited the position x minus 1 and y. Now this should be y, and this is not grid.size but grid0.size, and this is y, and that's fine. And here we're replacing the +1 here, and we're replacing the -1 there. Okay, and we also add that we haven't visited x and y +1, and we haven't visited x and y -1. Okay, so we mark the current node as visited. We visit all of its neighbors unless they have been visited before. And then this will visit like a whole island. It will visit all of the neighbors we haven't visited until it can't explore no more. We need to check for another thing. And that is if it's a 1, if it's land. Because if it's a 0, we don't visit it. So, and visited x +1 y is equal to 1. Actually, this is a char, so it's equal to 1. And visited x -1, and y is equal to 1, and visited of x and y +1 is equal to y, not to y, to 1, and visited of x and y -1 is equal to 1. So we visit it as long as it's within the grid, we haven't visited it before, and it's land. And we explore all of it. So now we can get rid of these. And so we basically go over int I equals 0, I less than grid.size, I ++, int O equals 0, O less than grid0.size, O ++. And so we're iterating over the entire grid. We have a counter because we have to return the number of islands, so num islands is going to be equal to 0. If grid I O is equal to 1 and we haven't visited it, then we add num islands. We add 1 to num islands, and we do a DFS over grid IO. And at the end, we return the number of islands. Okay, so just to recap, we are keeping a visited vector that we reinitialize every time we call this function. We start the number of islands at 0. We go over every possible position in the grid. If it's a 1 and we haven't visited it, we increase our number of islands, because that's a land we haven't visited before, so it has to be an island. And we explore that whole island, right? With this DFS that explores all its neighbors as long as they haven't been visited it and their land, and that they're in the grid. Otherwise, if they're 0 or if they haven't visited before, we don't do anything, and we return at the end the number of islands. So let's run that bastard. No viable overloaded, but well, so this is a vector of bool, not a vector of char. I got confused. Num islands, not num island. Okay. So I did something wrong. So went into there 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. So all of the times basically. Same with this. 1, 2, 3, 4, 5, 6, 7. Okay. What did I do wrong? So let's see out there and then check. Check 0, 0. And then it doesn't go into any of these. Why doesn't it go into any of them? Oh, this. It should be grid, not visited. Ah, okay. I don't know my rejects, I guess. Grid. There we go. Okay. So a bunch of misspellings. Just in case. Let's just do that. And we submit. And there we go. Easy peasy. Orange squeezy this time. Okay. So we're done number violence, and now we do rotating oranges. We're right on time. And we're gonna even end a little bit early. So the reason why I said these two problems are like good to do back to back is because they're pretty similar. We'll find that out in a second. So let's read this problem. It says 994 rotting oranges. I almost said rotating. You are given an n by n grid where each cell can have one of 3 values. 0 representing an empty cell, 1 representing a fresh orange, or 2 representing a rotten orange. Right? And this time they give us a picture. Every minute, any fresh orange that is 4 directionally adjacent, so up, down, left, right, to a rotten orange becomes rotten. Return the minimum number of minutes that must elapse until no cell has a fresh orange. If this is impossible, return -1. Righto. So what we do is there's 2 parts to this. Okay, so let's do a drawing. Yeah, I guess. Okay, so it shows us right here. We start, this is the rotten orange. Minute 1, both of these get infected. Minute 2, these 2 infect these 2. Minute 3, this one infects this one. And minute 4, this one infects this one. And then they're all infected. right? There's also the case. So okay, let's start with one important fact here that's gonna come in part 2. Let's say we don't know how to simulate this yet, but there's a part here where it says if this is impossible, if it's impossible that all oranges become rotten, there's no fresh oranges, return -1. How do we know? By looking if there's if it's impossible, and we can know that by looking like really easily. And this is sort of related to our problem with the islands before. So let's say, oh, let's say this is my grid, right? And I have an orange here, and I have an orange here, and an orange here, and I have an orange here, and I have an orange here, and orange here. Okay, and let's say this is rotten, and this is rotten. Can you easily tell me if they're all gonna become rotten? Yes, and the reason why is if you think about this like as like islands. So this is one island, this is one island, and this is one island, right? And they have to be connected in order for fruits to be infected, right? So if we have a rotten orange here and a rotten orange here, that's a rotten orange in this island, and that's a rotten orange in this island, these islands are all going to become rotten eventually because they're all connected. So it's going to spread and spread and spread all through the island. However, this one is not connected to anything and is not rotten, so it's not going to become rotten at any point because it's not connected to anything, right? Like if you think about it like cheese and mold, if you have some cheese, like a bunch of like, if you have some cheese with mold in like one side, and then you have cheese with no mold, like it's not connected, so it's not gonna, mold's not gonna stick to the other cheese, right? Same with this, like your rotten oranges, this is when it's not gonna become rotten because it's not connected to rotten oranges. So if an island doesn't have any rotten oranges, that island will never become infected. That is the fact that we're gonna use here. And now, how do we simulate the infectedness? So you could think, oh well, let's do it similar to what we did on like last problem, which is do a DFS. So like you start here, and then you spread to all the neighbors and their neighbors. So you go here. Does it have any neighbors? No. So you go back and check the rest of the neighbors here. You go here, and then okay. So you know that that's how you detect the islands or all of the oranges that are going to become rotten. But this problem has an extra complication, and that is that you have to return the minimum number of minutes that must elapse until no cell has a fresh orange. In other words, you have to return the what is it? The minimum distance between the biggest island, or no, the minimum distance between the rotten orange and the furthest border in any of the islands, right? Let me try to phrase that differently. So let's say you have two islands here. You have one that's this, and this is the rotten one, and then you have one. Let's make it separate. That's this. So the time that it's going to take for all of them to become rotten, this one's going to be 1 minute, and 2 minutes all of them are going to become rotten. This one's going to be 1, 2, 3, and that's going to be happening simultaneously. Like it's not like you're going to go this and then that one. It's going to be happening simultaneously. So the farthest an orange is from its border, the longer it's going to take to get there, and it's always going to go in the minimum distance possible. So it's going to go in like a straight line. So for the minimum amount of minutes that it's going to take for all of them to become infected, you have to find this longest section, and you have to find the minimum distance between this and this, right? Now that is a more complicated problem than what we're going to end up solving. And And how we're gonna end up solving this is not with DFS, but with BFS. BFS has an interesting characteristic that DFS doesn't have, and is that it lets us calculate the minimum path between a point and all of its neighbors, or all of its connections, between a point in a graph and all of its connections. It calculates the minimum path, as long as it's all of the connections are weight 1, right? If you start having weight 15 and weight like 5 or something like that, then BFS doesn't really work anymore. You need to do something like Dijkstra. But for a 1-0 graph, which means that you have nodes that are connected and the edges represent the distance of 1 always, a BFS finds the minimum path. So we care about finding the minimum path, so we're gonna use BFS. And then we're gonna use a technique that I used in a previous stream, I don't remember for what problem, to be able to figure out how many seconds. Which is basically like figuring out the amount of rounds. So a round is, how do I explain it? A round is a second, basically, a minute. So this is minute 0. And at minute 1, what's gonna happen? This is gonna get infected, and this is gonna get infected. So that's another round. At minute 2, what's gonna happen? This is gonna get infected, and this is gonna get infected. This is 2. And at minute 3, this is gonna get infected. This is minute 3. So we're gonna simulate those rounds using a BFS. Okay. So I'm not gonna like whiteboard a lot longer. Instead, I'm just gonna go solve the problem, because I think it's a little bit easier to explain with the code. It's 994, not 998. Okay. So to do a BFS, you need a queue. So we're gonna have a queue of a pair of int that is going to determine the next position that we're going to visit, right? And then we push into our queue the position. Oh, well, we don't do this yet. So now we need to find all of the rotten oranges, and those are going to be our starting position. So we're going to add those to the queue. So we iterate over the entire array. So we're cycling over an entire array, and if so 0 is an empty cell, 1 is a fresh orange, 2 is a rotten orange. Okay, so we're gonna find all of the rotten oranges. So if grid I o is equal to rotten, which is 2, then that's gonna be an initial position in our queue. So we're gonna do queue.push I o. Okay, so now we have all of the initial rotten oranges in our queue. And so now what we're gonna do is, while our queue is not empty, this is just regular BFS. If you haven't done a lot of BFS, I recommend you do some problems and you learn how it works and how to write it from 0. Like, I don't have this memorized, but I know in general how you do a BFS, so that's why I remember the syntax. And here's where the trick is going to come. So we're going to store our queue size here, and then we're gonna say we don't need an initializer. Well, queue size is bigger than or equal to 0. Queue size minus. So what we're doing here is we check the queue size at the beginning, and we're gonna do that many iterations because we know, okay. So at the beginning, we add these two rotten oranges, that's what we're done. And so our first round is just gonna be these two oranges. So we're gonna visit all of the neighbors of these two oranges. So we visit this one, like we add this to the queue because it's become run, and we add this to the queue because it's become run. So we do two iterations, one for each, for everything that was in the queue. Once we do the two, minute 0 has passed. Now, our queue size becomes whatever many elements we have, so it's 2 again. So we do another 2 iterations, which were the elements that were added on the previous run. We process them, and that's going to be minute 1. And then these become infected, all of the neighbors. There's 2 elements here, so we're going to do 2 iterations. They become infected, and that becomes, sorry, not 2, but 3. Sorry, not 3, but 2. And then we have only one to explore, which is this one. And we explore the one, and that's going to be our minute 3. So we're simulating the minutes with BFS. This is like a BFS trick to know like how, like, you basically calculate, like, this helps you find out what distance you are from the epicenters where you started from your original starting position. And sometimes you have multiple starting positions, so that's how you keep track of them. And then so num seconds is going to be equal to 0. And then once we do this iteration here, that's going to be 1 second. So we do num seconds plus plus. Now, how are we going to do the iterations? We're basically going to pop auto x, y are going to be equal to q.front. We're going to pop the front of the queue. And now that we have x and y, what we are going to do is we're going to explore all of its neighbors. So I'm going to steal the logic from the previous problem, which I don't remember what it is. This one. I just got that. Okay. So we're going to copy this logic here. But instead of exploring with a DFS function, which is normally recursive, this is more of an iterative solution. So we're going to need to do multiple steps here. Do we need to do multiple steps? Yes. No, I don't think we need to do multiple steps. So let's just leave it as is for now. So this stays mostly the same because 1 is a fresh orange, so those are the ones that we can visit. Ooh, and a fun thing we can do here is instead of having visited, we can remove all of these conditions. And that is because, I'll show you in a second. Because we're going to keep track of which ones we visited through the number that is on them. So once we visit an orange in a grid and we make it rotten, we're going to update the value basically. So here, once we pop the position, we're visiting this orange. That means it's getting infected at this second. So we're going to say grid x, y is going to become 2. And we're only going to visit the ones that are fresh, that are adjacent. So, like so. Now, instead of DFS, we're going to say q.push x plus 1, y. Right? Let's do, oh. Whoop, 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 whoop. Now we update these values. Okay. We're gonna basically push those. So before we had like a if we visited check, now we don't need that because we're marking them as visited by changing the value in the grid. And every step of this is gonna be a minute. So we're gonna do it for all of the things in the queue, and that's gonna be one of the steps. We increase our seconds, and then all of those that were added, and then all of those that were added. Each time we add a series of elements, that's gonna be a step. And at the end, we can't just return num-seconds. And the reason why is because of that second condition that we have there, and that is if this is impossible, return -1. So at the end, we have to check if there were any islands that went unvisited, basically. So we can basically just copy this, and if there are any fresh oranges, we return -1. This means there's a fresh orange left still that we didn't change. Otherwise, we return them seconds. Okay? This looks right to me, but I'm sure I made a mistake somewhere. I did. This returns 0 and it should have returned 4. This returns 0, should return. Okay, so I'm not increasing my num seconds, but I am. Does this not work? I don't do that syntax too often, so I'm not sure. Oh. Do I have to add the variable? Oh, it doesn't even go in. Oh. Oh, we have ints this time. We don't have, okay. So, we're gonna basically do this, and then we're gonna do that. I don't know if what I did, if I did it properly, because I did it pretty fast, but char, where did it error? Addition of unsigned offset. So size 11. Oh no, size 1, size 1. Because we start, this is the example I guess it starts with. It's in vector, so it's some vector operation I'm doing. Ba, 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 ba. It was erroring out after spitting out the 0, which, where was it? It can't have been that one. There was something else I was printing. Okay, let's... No, those are submissions. No, this is what I submitted. Okay, so 1, 1, and then 0. What does this mean normally? Bigger than 0 is bigger than or equal to 0. This is the other question. Do we think it's because of this? I mean, I doubt it because it would for the rest of the iterations, but... Okay. We say we're taking 1 more second than the output. Why is that? Can we just return num seconds minus 1? You think? Okay, let's see the first example. 1, and then 1, and then 2, 2. What are we printing? This should probably be x and y. So we're gonna do x and y and line, and then this is gonna be and line. Okay. Okay, so we do 1 at 0, 0. Then we do 2, 1 at 1, 0, 1 at 0, 1. Then we do 3. 1 at 1, 1. Ah. One at 1, 1, 1 at 1, 1, and 1 at 0, 2. Okay. And I think I've had this problem before. But okay, so we visit this one and this one. Then one of them has to go first and add it. Okay, so what we're doing wrong here is we're doing this at the wrong time. We should be doing it when we add that to the queue. Because otherwise we add, so otherwise what happens is we visit, let's say, what is it laid out? Yeah. So we visit this one, right? Then we visit this one and this one. And so when we visit this neighbor, we add this one, right? And when we visit this neighbor, and we haven't changed it because we haven't visited this node yet. When we visit this one, we also add this one because we don't know that this one we already visited technically by another node. So we need to do this, the visiting part, when we push them to the queue. Joe. So we're gonna do that. Oh, this is already 2, so that's fine. We don't need to do it for the first iteration. But we do it in here, so we did need the brackets, which is kind of annoying. So, here, grid x plus 1, y is going to be equal to 2. Same with this, but x minus 1. Same with this, but y plus 1. And same with this, but y minus 1. So we visit them when we are adding them to the queue, not at the point of visiting, because otherwise we add something twice. There you go, now it works. If there's fresh oranges. Okay, well, if we can just do a case for that. If q.empty just return 0, because there are no rotten oranges in general. I don't think I copied it. Okay. Let's use this test case just in case, so we're not losing time. Okay, and then we submit. Wait. So I have to think about what these mean. So if there's no fresh oranges, The minimum number of minutes that must elapse under it until no cell has a fresh orange. So if there are no fresh oranges at all, then it's 0. But if there is one fresh orange, it's such a weird case. Okay. Okay, so I'm very tired. I can't really think through this. Basically, if we see a fresh orange, return -1. But if we see no fresh orange, no oranges in general. If we see no oranges in general, then we also return, we return 0. So int num oranges equals 0. If grid I o equals 0, equals 2, num oranges plus plus. Num oranges plus plus. If not num oranges, if there are just no oranges, we return 0. And then we don't need that QMT, but I think I removed it already. Wait, let me add that test case. Okay, I think we're good. There you go. Very nice. Alright, let's write down the comments for the ideas really fast, and then we're done. Idea. BFS helps us find the shortest path from run orange to all adjacent oranges. Therefore, we can find the minimum time across all oranges. This doesn't really explain a lot of how BFS works and everything, but you can just probably look a video. Add rotten oranges to queue to start. BFS trick to count distance time from beginning points. Visit, so mark as run before visiting, so we don't have the same orange twice. And then if there's any non-rotten oranges, return -1 because we can't reach them. If there's no oranges at all, then it takes 0 minutes to infect all fresh oranges. Okay, and now we go to 200, and here idea, run DFS on every unvisited cell. DFS will explore the whole island. Every time we find an unvisited cell, that means this is a disconnected piece of land. Disconnected land, increase islands. And then this is pretty self-explanatory. Okay. Okay, we do get status, we do get add period, we do get commit -m, add solutions from console logs. I think it is 25. What is this console logs? Yeah, 25. Perfect. And then get push. All right, perfect. Okay, that's gonna be it for me. Thank you everybody for joining. And I'll see you tomorrow for another stream where I'm gonna be doing my project again, the RAG project. All right, I'll see you on the next one. Have a great Friday and rest of your